Ever since I was a young boy, I was always curious about how things worked. I was fortunate enough to be surrounded by art and design that inspired me to look at things in a different way. This led me to pursue a career in product design. And over the past few years, I've discovered that rather than trying to conceptualize an idea digitally on a computer, I prefer the classical method of sketching. Hand-making prototypes helps me visualize what I've designed. Every curve is exactly the way I want it, and it gives me a better feel for what I am designing. After graduating with a degree in design, my journey took me to the Royal College of Arts in London, where I did a dual Masters in Industrial Design and Engineering. As part of my final year, we were asked to just find a problem and find the perfect innovative solution for that problem. Fortunately or unfortunately, I had a bicycle accident which involved me falling off my bike at a low speed, breaking my 150-pound helmet which I was wearing at that time. Even though I walked away from that accident, it was only the next day that I realized that I had a concussion and had to be hospitalized for a few days. This made me wonder why my helmet didn't work, and I used this as a perfect problem for my project at the RCA. My goal was to make the most safest helmet we could ever make. Looking into nature, the woodpecker is one of the only species that experiences severe impact to its head every time it pecks. Its beak and skull are joined together by a corrugated cartilage structure that absorbs each impact. Let's not forget that the speed with which this bird strikes the tree is almost 10 times per second. This inspired me to look at materials which would mirror the qualities of the woodpecker and which can be used as substitutes for expanded polystyrene. Cycling helmets really haven't changed much in the past. EPS has been the core liner for practically every helmet made in the last 3 decades. Improvements have been made in areas of styling and aerodynamics, but safety was always taken as a given. Extensive literature exists to show that cycling helmets are not always as safe as they're portrayed. In fact, if you look at the testing standards, you'll notice that they have varied so much in the last few years. Any helmet which can withstand a maximum force of 250 Gs meets today's European standards for safety. If you think about it, that's a monumental amount of impact which is allowed. Kranium helmets are made using a material called dual density honeycomb board, which is actually made from paper. For example, if you look at a magnified version of the board, you'll notice that the honeycomb cells act as tiny little airbags when sealed together to form the board. The structure of the helmet itself is designed to allow flexing at different points. For example, if you look at this part of the helmet, it doesn't flex at all, whereas if you look at this part, it actually allows a lot of flex. This flexing absorbs the peak force of the impact, after which the tiny air pockets absorb the remaining energy by crushing. So, for example, when you look at an EPS liner, it can only accommodate 2 mm of crushing, after which point it starts to crack and then breaks. Once it breaks, it actually stops doing its job. In comparison, the Kranium liner has been designed with a significantly larger crushing threshold of 8 mm, where each honeycomb cell acts as a separate air cushion. This structure results in 90% of the liner being air, making the Kranium liner 15% lighter than standard EPS helmets. Due to its superior crushing ability, the liner can also be made much thinner than EPS shells as well. A lot of people assume that once a product is developed, it goes straight into production. The reality is that there is a vast amount of work and effort which needs to be put in order to make such production viable. Being a safety product, development involves extensive testing in various specialized facilities across the globe. It might look simple, but a lot of specialized processes have been used to produce such a helmet. A series of codes and principles govern the placement and angles of the ribs to distribute the load. Once plotted, each individual rib is laser cut to maintain levels of precision. It is then assembled into a structural lattice, which then does the job of absorbing the impact. Being a paper-based product, waterproofing is of the utmost importance. Once assembled, the unit is submerged in a water-based waterproofing solution. This protects the shell from sweat, rain, and even fire. The Kranium liner passed the European standards for testing even after it was submerged in water for 7 days at the TUV test labs in Germany. To sum things up, the Kranium liner absorbs 3 times the amount of energy when compared to regular EPS helmets, making it a much safer helmet. At the same time, it is also 15% lighter than EPS helmets. EPS liners today are molded from petroleum-based products, whereas Kraniums are made from recycled paper, using absolutely no electricity. At the end of the day, it's lighter, it's stronger, it's just, well, safer.